Hello again from Digicool Things. In part 1, where I introduced my MECB based CreatiVision recreation, I ended the video with the CreatiVision Sonic Invaders game running successfully in attract mode. At that point, the next step was for me to create an interface to allow connecting a joystick so I could actually play the games. After a bit of research, I decided that I may as well implement a full CreatiVision Controller interface to support both left and right joysticks, as well as a keyboard. This would then allow full use of the CreatiVision software, including using the basic cartridge. I also decided why stop there. It seemed logical that if I was going to all the effort to create a full CreatiVision Controller interface for my CreatiVision recreation, that I should design it so that it also works with an original CreatiVision console. No doubt there are owners of original consoles who would like to be able to play the games with a more robust joystick and also be able to utilise a better keyboard than what the original controllers provided. So this is where my CreatiVision controller journey started. To start with, I already had the original CreatiVision schematics, so I was aware of how the console's controllers interface to the 6821 PIA. However, this had left an initial question in my mind, as I knew that the CreatiVision controllers included a 48-key QWERTY keyboard as well as 2 joysticks. From my past experience, it was immediately apparent that there was something extra going on. You see, the schematic shows the controller interface uses PIA port B and only 4 lines of port A, pins PA0 to PA3. For a typical scanned matrix keyboard, this would only allow a maximum of 32 key switches to be scanned, with a matrix of 8 rows by 4 columns, not enough for 48 keys plus 2 joysticks. So I did some research on the Creative Emu forum. This forum hosts an awesome group of CreatiVision enthusiasts. From the forum discussions, I was able to ascertain a number of crucial and time-saving pieces of information. Firstly, that the CreatiVision controllers use double pole switches. This dramatically increases the number of combinations possible in a simple 8x4 switch matrix. So 48 keys and 2 joysticks from an 8x4 matrix now made sense, although it certainly complicates the interfacing. Secondly, someone on the forum had already mapped the left and right controller port pins, which are used for each controller's keyboard and joystick switches. A spreadsheet was shared with their excellent key mapping results. A huge time saver, and crucial for someone who, at that point, didn't even have their own original CreatiVision console to study. Thirdly, a couple of members of the forum had already put together a PS2 keyboard interface, which also featured an input for 1 joystick. Their interface was based on an Arduino Nano board and a couple of MT8808 28-pin dual-inline package analog switch array chips. So, these 3 pieces of information provided all that I needed to be able to dive straight into my own design. Firstly, I decided that instead of using 2 MT8808 analog switch array chips, I'd instead use a single MT8816 analog switch array chip. The MT8816 provides an 8x16 array of analog switches, as opposed to only 8x8 array on the MT8808. So it's perfect for interfacing to the 2 controller ports of a CreatiVision console. Also, not only are the MT8816 still in production in a more compact PLCC 44 package, still retro-friendly thanks to through-hole PLCC sockets, they're also cheaper to source than just a single MT8808 in a dual-inline package. Secondly, I also decided that I didn't want to use an Arduino board in my design. Instead, I wanted a compact and cleaner solution designed around using an onboard microcontroller chip. Based on the number of I/O pins required, 5-volt logic, and my desire to stick with retro-friendly through-hole components, I decided to go for a retro-appropriate 8-bit microcontroller chip in a 28-pin dual-in-line package. Specifically, I really like the newer DA family of 8-bit AVR microcontrollers. Because I like a challenge, I also decided I'd start from scratch with developing the required controller firmware, including for the PS2 keyboard interfacing. This is mainly because most pre-written PS2 keyboard interface libraries are designed for use at a higher level. To most realistically interface a PS2 keyboard to the CreatiVision, it makes more sense to go to the lower level of mapping the actual key down and key release events of the PS2 keyboard to the CreatiVision controller's actual key switch closing and opening. This makes for the most realistic and accurate functional replication of the CreatiVision's own controllers, and therefore should be fully compatible with different software use of the controller keypads. Of course, whichever way you decide to interface a PS2 keyboard has its compromises. If you were to interface at a higher level by mapping translated keyboard ASCII characters to the CreatiVision's keystrokes, you could achieve a mapping of actual PS2 key characters to the CreatiVision key equivalents. But this would be at the compromise of not truly replicating the actual key presses and key releases of the individual key switches in the original controllers. By instead interfacing at a lower level, we can accurately replicate the original controller key actions, but with the compromise that we must allocate an actual PS2 keyboard key to be the equivalent of a CreatiVision key. This is fine for the majority of keys, but some keys, for example the colon and semicolon, are on separate keys on the CreatiVision, but are a single combined shifted key on the PS2 keyboard layout. But I consider this the lesser compromise. It is much more important to replicate the actual CreatiVision key actions. Non-matching PS2 keys can either be remembered, relabeled, or even a custom keyboard implemented. But more on that later. So with my plans now solidified, it was time to start on writing the firmware and also some breadboard prototyping. I decided to start with the PS2 keyboard interfacing, as this was core to the overall controller interface functionality, even though I just wanted to play a game of Sonic Invaders. First off, I decided on an interrupt-driven keyboard interface as being the only way to go. Interrupt-driven enables writing a 100% reliable keyboard interface. So I started by writing an interrupt handler to receive properly formatted PS2 keyboard scan codes and store them in a circular buffer for subsequent access by the main controller program loop. Here's the interrupt service routine that I came up with. The interrupt routine is triggered by the falling edge of each PS2 clock signal transition. I then capture all 11 bits of a PS2 scan code transmission and then verify the transmitted scan code structure to ensure that I have an appropriate level start and stop bit, and I also calculate the parity bit to ensure it is the correct odd parity, in addition to capturing the 8 data bits. Only with a valid received scan code byte do I then store it in the retrieved scan code buffer. Pretty robust. Now to debug this code on my AVR microcontroller chip. So I hooked up an AVR microcontroller's 8-bit port A to one of my 8-bit LED things, and I wrote a very simple main application loop that simply retrieves the next scan code from the buffer and outputs it on port A, then delays for 1 second. Therefore, I can see all of the captured key presses and key releases displayed sequentially on my 8-bit LED thing, so I can assess if my code is working correctly. So let's take a look at that. So here's an example of using my 8-bit LED thing for debugging. You can see on my breadboard I've got an AVR chip and an 8-bit LED thing just linked to port A. I've also got the MP Lab snapboard, which I use for programming the AVR chip. Has a single wire, well, apart from the power, has a single wire for the UPDI programming. And lastly, I've got a mini-DIN 6-pin PS2 keyboard connector, connecting a couple of ports to a PS2 keyboard. So the keyboard input is interrupt driven. At each interrupt I'm retrieving the scan code and putting it into a keyboard buffer. So for debugging, I've got a little loop that just reads what's in the keyboard buffer and outputs it to port A, so it displays on the LED, and then I delay a second and loop round. So basically whatever comes from the keyboard goes into the buffer, and then I'm displaying the buffer 1 entry per second on the LED. So if I try that out, if I press key 1, you've just seen 3 codes. So key 1 is 1, 6 in hex. So when I press the key down, it does a 1, 6 code. And then when I release the key, I get the F0 release code followed by the key, which is 1, 6. So pushing the key down and releasing it, I get a total of 3 codes. If I try with button 3, you will see I get 2, 6, and then release, and then 2, 6. And for the last one, we'll try button 2, which is 1E hex, followed by F0 1E for the release code. So my 8-bit LED thing has been really helpful with the debugging. With this proven, I then dived into designing my first prototype PCB. In the distant past, I always fully developed and proved new digital hardware on a breadboard prototype before moving to PCB design. That was just the way we had to do it back in the day, when PCB design and PCB manufacture was time-consuming and expensive. These days, with the advent of great free PCB design tools like KiCad and cheap PCB manufacture, it actually now makes more sense to go straight to the PCB design stage for your final prototype design. This also fast-tracks your project by getting into the PCB design stage earlier, even if several revisions are required. Now, this project turned into one of those several revisions required exercises. For my first PCB revision, I was caught out by a few, let's call them oversights. Firstly, I made the incorrect assumption that the CreatiVision key mapping, which I'd obtained in a shared spreadsheet from the CreatiVision forum, correlated to the controller connector pin numbers as labelled on the official CreatiVision schematic. Unfortunately, this was not the case. It turns out that the spreadsheet pin number references are the reverse of the schematic connector pin numbers. Here is the comments I've put in my source code to explain this. Essentially, for the two 10-pin controller connectors, pins 1 to 10, as shown in the CreatiVision schematic, actually correlate to pins 10 to 1 in the key mapping spreadsheet. So pin 10 in the spreadsheet refers to pin 1 on the schematic. Secondly, the KiCad mini-DIN footprint that I'd obtained for the PS2 connector via Mouser was reversed. As a result, the PS2 power pins were reversed, resulting in me frying my only compact PS2 keyboard. So a replacement keyboard had to be ordered. Lastly, I completely missed the illogical sequence in the switch matrix address truth table in the MT8816 datasheet. This one actually left me completely gobsmacked. I always thoroughly read datasheets. They're a designer's bible. But this one got by me, as it makes no sense at all. The truth table anomaly is only highlighted by an asterisk and a vague comment. Furthermore, the only reason that I can ascertain for this anomaly is that the IC's pinout must have already been published and locked in. Otherwise, it would have been much more logical to just relabel the pins so that the truth table was in the expected logical sequence. Anyway, for this last oversight, I ended up resolving the illogical mapping in software, therefore retaining the logical PCB MT8816 pin labeling sequence. But the first two oversights did, however, require a rework of my schematic, software and a rework of the PCB. Having obtained my second prototype PCB, and with some more work refining the software and manually remapping all of the spreadsheet key mappings to their actual CreatiVision schematic controller port pin numbers and their associated PIA port pins, I finally had a working prototype. Lastly, I further revised the PCB to revision 1.2 to include a header for the PS2 connections, more on that later, and also a header to determine if we are using the hardware reset circuitry, which I had included in the schematic. As it turned out, I can effectively software reset the MT8816 switch array on power up, and I haven't once needed to reset my microcontroller during my testing. I've kept the hardware reset circuit on the PCB just in case, but essentially it doesn't need to be populated. Okay, so let's look at my eventual revision 1.2 schematic. As you can see, it makes for a quite compact, basically 2-chip only design, catering for both original CreatiVision Console connection and also for use with a direct PIA connection for CreatiVision recreations, like my MECB system. For supporting recreations, I effectively have duplicated the original CreatiVision's PIA port diode isolation and pull-up resistors on my controller interface, allowing it to be connected directly to a PIA's port B and PA0 to PA3 of its port A. So it's perfect for interfacing straight to a PIA for any CreatiVision recreation. The PIA port connector that I've used matches my MECB Motorola I/O card 24-pin IDC connector, which carries all of the PIA ports and also ground and 5 volts. This allows my CreatiVision controller interface to also be powered directly from the MECB Motorola I/O card itself. For using the controller with a real CreatiVision console, I've included a USB-C socket power module for a USB-C power source, and also, crucially, a ground reference header pin connection. Unfortunately, the CreatiVision console's controller ports do not include a ground reference. In addition, the CreatiVision's AC power supply is not earthed, so the only chance of a common earth reference ground would be perhaps via your display connection. For reliable use, you therefore need to connect the ground reference header to your CreatiVision console. To do this externally, there is a ground pin available on the CreatiVision's left side cassette deck connector. As a warning, apart from earlier frying a PS2 keyboard, I also managed to damage one of my MT8816 chips when I forgot to ground reference the connected devices. Everything was working for a few sessions, then perhaps I connected up or powered up in a different order, as a number of keys stopped working when I powered up one day. It appeared I had managed to damage one of the MT8816 switch ports, which could have only been due to the floating ground level between the two devices. Since then, I've ensured the ground reference is connected between the CreatiVision console and my CreatiVision controller interface, and I've had no more problems. I imagine another option, instead of the side connector ground connection, may be to investigate whether you can install the controller inside the CreatiVision Console's case, although it'd probably be a tight fit. Or alternatively, solder in a ground connection wire or connector to feed from the back of the console. But it's really over to you. Just make sure your connected devices share a common ground. So let's now take a look at the latest revision 1.2 PCB layout. Here's a 3D render of my PCB. I think it looks really awesome, but then I do really enjoy and spend too much time on PCB layout. As you can see, there's plenty of silkscreen labels to clearly identify all of the connectors. Everything is through-hole for easy assembly, with the exception of only two surface mount components. These are the two large, ultra-low forward voltage Schottky diodes, which isolate the two alternative power sources. Although these are surface mount, they are plenty big enough to allow for very easy hand soldering. The Atari Joystick DB9 interfaces also have jumpers for selecting a second button connection on either pin 5 or pin 9 of the DB9 connector. On an original Atari joystick or a C64 joystick, these pins are normally the analog pedal controller inputs, but on some later DB9 joysticks, these are used for a second or third button connection. Often these joysticks have a switch to allow enabling or disabling these extra button connections. The original CreatiVision Controller joysticks have two buttons, so a simple two-button capable DB9 joystick is recommended if you have one. Other than this, note that the original CreatiVision joystick supports 16 directions, whereas an Atari DB9 joystick only supports 8 directions. Whether this really affects your gameplay is probably subjective, but I'm okay with it. The other thing of note that I'll mention is that I've also written the firmware to be as low latency as possible. Specifically, there are absolutely no software delays implemented in my code, anywhere. Joystick actions and keyboard key presses are serviced in a tight loop. So when you use the joystick, your joystick actions are translated to CreatiVision joystick switch actions virtually instantaneously. Also, when you press a PS2 keyboard key, the only latency before the CreatiVision keyboard key is also engaged is the time taken for the PS2 scan code transmission from the keyboard for the key down or key release event. Perfect. Okay, so on my desktop you can see one of the first revision 1.2 PCBs, fresh from manufacture. I'm pretty confident it'll work first time, as it's just a fine-tune from my revision 1.1 prototype, as I've already described. So let's get one assembled. And here is the first partially assembled board, with its two main chips installed and just the reset jumper to ground, as I haven't installed the reset circuitry. I also haven't yet installed the diodes and the pull-up resistor network to support my CreatiVision recreation. This is because I thought I'd start off by showing the minimal assembly required for use with a real CreatiVision console. If you were only intending to use this controller interface with a real CreatiVision console, then the diodes and resistor network are not needed, as I've clearly noted on the PCB silkscreen. Okay, so let's try the controller with a real CreatiVision console. I missed the opportunity to get my hands on a CreatiVision console a few years ago, which is what also prompted me to explore my old TMS 9929 chips, develop my alternative low pin count VRAM solution, and also to make my MECB based CreatiVision recreation. But as luck would have it, and very timely for my current project, recently another CreatiVision console came up for sale locally. This was the first one to appear on my watch list for several years, so I jumped on it knowing it's just what I needed for final testing of my new controller interface. So let's get my CreatiVision Console wired up. Right, so the CreatiVision Console is on the bench. It only just fits in because of my limited camera space. As you can see, I've plugged in a couple of 10-way DuPont jumper leads to the controller port pins to connect across to the controller PCB headers. And as discussed earlier, don't forget a ground reference connection to your console. I've also used a USB-C power feed to power the interface board. Finally, I've also plugged in a PS2 keyboard and a joystick into the left joystick port. Okay, we're ready to go. Let's turn on my monitor camera and I'll power on the console and let's play a game. Unfortunately, the composite video output of my console is quite noisy on this video monitor. I probably need to upgrade it with a TMS RGB module, but it'll do for this demonstration. So if I hit reset, now I can press number 6 on the keyboard and that starts a game. Then I can use my joystick. Away we go. Pretty bad. But it's all working. Okay, let's switch off and I'll change to the basic cartridge, which is off, on, on. So that should be basic. Let's turn it back on and have a look. Okay, we've got basic. And I can hit some keys on the keyboard. 2, 3, 4, 5, 6, 7, 8, 9, 0, Q, W, E, R, T, Y, U, I, O, P, A, S, D, F, G, H, J, K, L, Z, X, C, V, B, N, M, comma, dot, slash. Enter. So our keyboard's working as expected. If you're a real console owner, you might have already noticed I have a mega cart plugged into my console. I made myself a new mega cart for the CreatiVision Console, which includes all 3 of the original video technology diagnostics. Noting that Diagnostic C was just recently recovered and shared on the CreatiVision website in August 2024. I've revised the schematic and PCB layout of the earlier published MegaCart, revising it to version 1.2. You can find my revised MegaCart KiCad schematic, PCB design and Gerbers on my GitHub, together with a full description of my changes. The repository is forked and revised from the original GitHub project and licensed under the same Creative Commons Attribution and Share-alike license. With all 3 diagnostics available in my new MegaCart, I can also switch to the Controller Diagnostic B for controller testing. So let's take a look at that. I'll switch off again. Okay, Diagnostic B, I've got all the switches off except for switch 1. And we should be in Diagnostic B. Let's apply power. Okay, now I can show you all the buttons. If I hold button 1 down and then release, button 2, release, button 3, release. So the keyboard is working fine. Left arrow, A, S, D, F, G, H, J, K, L, semicolon, Z, X, C, V, B, N, M, comma, dot, slash, and spacebar. We have shift, and if I grab my joystick, we have up, we have down, left, right, angle is the 4 angles, and fire. Okay, with the controller tested on a real console, I'll add the CreatiVision recreation supporting components. Let's do that now. Okay, so as you can see, I've now added the 16 diodes, resistor network and the 24-pin IDC connector to support CreatiVision recreation direct PIA connection. As a recap, particularly for anybody new who hasn't been following along with my MECB project, let's take a quick look at the MECB components of the project. Here are all the cards laid out. First, we have the MECB backplane, which provides the card mix and match capability for building an MECB based system. Then we have the Motorola I/O card with sound. This features the Motorola PIA chip, ACI chip and also the Motorola PTM chip. In other words, a parallel and serial I/O as well as 3 timers. In addition, it has an SN76489 digital complex sound generator. For the CreatiVision recreation, we're only using a 68B21 PIA and the sound chip. So you could leave the 6850 ACIA and the 6840 PTM chips unpopulated. Let's plug that into the backplane. Next we have the TMS VDG display card. This was designed with my low pin count alternative VRAM solution that I devised. See my earlier blog posts and videos if you're interested in this journey. The card also has an audio pass-through socket to allow feeding the sound chip's output through the video output connector. So let's get that plugged into the backplane too. Next, we have a MECB 1MB bank switched ROM expansion card, which enables switching up to 16 banks of up to 64K of ROM space. At the moment, I've just got one 512MB ROM installed, which allows 8 banks to be switched between. So let's plug that in. Finally, we have the 6502 CPU card. For this project, I've left off the ROM, as the ROM is all handled by the 1MB ROM expansion card. So let's plug that in. So, there is our MECB based modular hardware with its memory map configured for our CreatiVision recreation, as presented in more detail in part 1. For my MEC based CreatiVision recreation, I've also made up a 30cm IDC24 1-to-1 cable to connect the new controller interface to my MECB Motorola I/O card PIA connector. As mentioned earlier, this connection also powers the CreatiVision Controller PCB. Let's plug that in. As before, I'll also plug in a PS2 keyboard and a joystick to the left joystick port. Now there's one more discovery I made, which I'd initially overlooked when studying the CreatiVision schematic. That is, that the CreatiVision's reset button, which must be pushed in order to start a game, is actually connected to the 6502 NMI input, the non-maskable interrupt. It is not actually a hard reset. Because of this, I initially wired up a NMI link jumper cable via my MECB prototype card header. However, this was only a temporary stopgap measure to get me up and running. A non-maskable interrupt link wire is not really ideal, particularly since your NMI interrupt button should really be debounced. So to properly resolve this, I've also made an update to the existing MECB 6502 CPU card to add a debounced NMI push button and NMI button header. To join the existing reset push button and reset button header, this was covered in my last video. But please note, since making the updated 6502 CPU card and making that video, I've posted a follow-up on the linked blog post. Essentially, during my testing of Sonic Invader, I noticed that the CPU card hard reset button also did actually work for getting me into play mode. However, this doesn't detract from the fact that the original CreatiVision Console only has an NMI button for reset. So, to ensure full CreatiVision software compatibility, and for other projects that might require an NMI button, I'm still happy to have now implemented a debounced NMI push button on version 1.3 of the 6502 CPU card. Anyway, here's a 3D render of the updated 6502 CPU card PCB. So let's connect up the power. Also the video and audio leads. So let's power up and test it out. I've loaded a few different CreatiVision ROMs into my MECB 1MB ROM expansion card. Currently I'm bank switched to the Sonic Invader game, as I'm keen to have another game on the really sharp display output of my MECB VDG video display card. Now, as mentioned previously, from the initial track screen, I first need to issue a reset or NMI interrupt. So let's do that. I'll hit NMI. So we're in gameplay mode. Then based on the game's keypad overlay, hitting either the 6 or B key on the keyboard starts play. So I'll hit 6. And I'll grab my joystick. See, a bit of sound would help. Okay, that'll do for now. It's awesome finally playing Sonic Invaders again after all these years, but this time on my MECB based CreatiVision recreation and with a good joystick and awesomely sharp display. Now, another lesson. This one is about the classic saying RTFM. You see, during initial testing I thought I had a problem of the aliens occasionally disappearing from the screen. I thought I had a hardware issue with my display card and started swapping DRAM and TMS VDG chips on my display card. It was only when I noticed a pattern to this issue that I finally RTFM. You see, I originally thought pressing the fire button before starting was incrementing the number of credits for gameplay, just like an arcade board. But it turns out that this was actually selecting one of 16 game modes. I was incrementing the count to 5 before starting a single player game. Fortunately, I finally noticed that the aliens didn't randomly disappear if I started the game with a 1 count. Reading the manual was the answer. It turned out that Mode 5 was where the aliens disappear for periods of time, to add a new challenge to the game. So, problem solved, there was no problem. Okay, with Sonic Invader gameplay tested, let's now swap across to the Diagnostic B cartridge that we demonstrated on the original console to do the CreatiVision Controller test. Okay, so I'll switch off and adjust the switch for a different bank. Switch on, I'll hit reset or NMI, and we have our Diagnostic B. So I can press 1, release, 2, release, 3, 4, 5, 6, 7, 8, 9, 0. Control key. I think the control key and the fire button are shared. Then there's Q, W, E, R, T, Y, U, I, O, P. Enter. Left arrow. A, S, D, F, G, H, J, K, L, semicolon, right arrow, which is also one of the buttons on the joystick, Shift, Z, X, C, V, B, N, M, comma, full stop, slash, and space. And I can try the left joystick. So I go up, down, left, right, diagonal left, diagonal right, diagonal down the other direction, and switch, or fire trigger. So, all works great. So I've got to say I'm really happy with how my CreatiVision Controller project has come together. If you'd like one, I've now added the CreatiVision Controller to my Tindie Store. So you can order just a PCB, or there are several optional packs to complete your controller kit set. I've also made the firmware's C source code available via the Digicool Things GitHub. I'm pretty thorough with documenting my source code, so it should be pretty easy to follow. Now, just before I finish this part 2, for those who are still watching, let me say it, there's one more thing. There may well be a next part in the future for my CreatiVision Controller journey. As a teaser, especially for CreatiVision enthusiasts familiar with the original CreatiVision moving key keyboard accessory, I'll leave you with a sneak peek of what I've started working on, and the reason for adding a PS2 keyboard header to the version 1.2 PCB. The keycaps that you can see take advantage of my previous experience developing and optimizing my hexadecimal MX keypad, also on my Tindie Store. This has allowed me to make some quite impressive and very familiar looking, to a CreatiVision enthusiast, Cherry MX key switch keycaps. That's it. Thanks for watching.